Hello again, guys, ladies and gents. Another exciting video. Dude, just kidding. This is not very exciting. This is quite theoretical, actually, or at least the idea of lattice energy is kind of an abstract idea we use to describe how strongly a salt, an ionic salt, is holding together, perhaps, or perhaps the energy released as gaseous ions fall together to make a salt, which we've never really seen exactly. But anyways, here's the general form, and then let me give some specific examples. Boy, I'm going to have to shrink this down quite a bit to get that to fit in my window. But let's see if I can do some pointing here. Man, that's a long story, isn't it? So the story kind of begins right here with a metal and a non-metal. M for metal, X for non-metal. Oftentimes the non-metal is a diatomic molecule. Chlorine, fluorine, oxygen, nitrogen even. Iodine perhaps is a solid. And we want to react that to measure the delta E or delta H. We use them almost synonymously. In our course, pretty much totally synonymously. But we'll talk more about that in a later chapter, second semester, I think. I go directly from there to here, taking 1 mole of this and 1 mole of this to create 1 mole of this solid. But what I really want to think about is the steps it might take, or imagine the procedure to go through to get from these elements in their standard states on the desktop into the gas phase ions. Oh, geez, I forgot my... Oh, no, I didn't. My gas phase ions right here. And as I have gas phase ions, they sort of fall down the energy hill to create this metal non-metal salt. And to imagine that, I say, let's take the metal, the solid metal. Let me increase the size of this for a little bit for a while. Let me increase the, let me take the solid metal and melt it into a liquid. That's called the heat of fusion, to melt. To fuse, to melt, to freeze. Then I'll take that liquid metal and change it into gaseous metal. Metal gas, metal vapor. Sometimes we combine the delta H of vaporization and then delta H of fusion to get one delta H called the delta H of sublimation. To sublime means to go right from the solid to the liquid. I'm almost ready to take that, use that metal as a gaseous particle, atom, an atom in the gas phase, collection of atoms in the gas phase. But I really need to ionize it first, so I'll take this metal, ionize it once, perhaps that's it, but if it was like magnesium or calcium, that metal might like to ionize twice or even thrice, and I would add those two together, ionization energies, to get the metal in its positive gas phase form. Then I also have to break up this molecule of non-metal, X2, gas phase already, so I don't have to do anything with the phase, but I need to dissociate or break up that molecule X2 into the X atoms. Then also I need to give this non-metal an electron, sometimes 2. Because I broke up 1 full mole of X2 and it created 2 moles of X, then really the electron affinity is described as the energy change associated with the addition of 1 electron to 1 atom of that element in its gas phase. So really, since there's a 2 there, I'm going to multiply this times 2. You may be uncomfortable with that for a while, but chill. It's all going to work out once you see, like I said in the class, maybe 12 examples of this. You'll start to get the hang of it. So anyways, this step here finally takes the X, 2 moles of X to 2 moles of X minus and ions. And then, so, oh, by the way, this is quite measurable, this is 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 measurable, and even this is measurable, but this is not so easily directly measurable. It sort of is like the difference between this and the summation of everything else we've looked at. But we use lattice energy as a measure of stability. The greater the lattice energy, the more energy given off during this change, or the more energy difference between this and this, the more stable my salt, and actually the harder it would be to melt if I were talking about breaking it back up and going backwards. Taking that well, not only melt, but melt it and then push it up into the gas phase ions. So anyways, this term, my point is this term is usually by far the largest term, usually dominates this. So because this is so large, this will also be negative and probably large, and it's not easily measurable. Not easily measurable. Again, those terms look like this for this particular example. I had larger, the delta E or the delta H, also called the enthalpy change, energy change. This is to melt the solid, to boil the liquid, to remove ions from that metal, to break up the nonmetal molecule, to give that nonmetal molecule some give that nonmetal atom then some electrons. And this is the term we kind of want to get a handle on, electron affinity. Not always easily measurable, but definitely calculable. Let's go through a specific example. Sodium chloride. Yeah. Oh yeah. Okay, sodium chloride. There, you see it. So I start here and I end here. It's not too unreasonable to take 1 mole of this, half a mole of this if you're crazy. A full mole and a half mole would be quite an exothermic reaction, and we can measure this. We can also measure this, the energy to melt the sodium and to boil the liquid sodium, to gaseous sodium. And we can measure this, the energy to ionize the sodium from a sodium gas phase ion to a sodium gas phase atom to a sodium gas phase ion. I can also then measure this to dissociate the chlorine molecules. I started out, I'll say something about this. We don't usually balance equations with the fractions. I'll say something about that in a second. But if I had a half a mole of chlorine molecules would actually just give 1 mole of chlorine atoms. If I dissociate it, break those up totally. I don't know if that makes any sense, but chlorine molecules have 2 chlorine atoms per molecule, so half a mole of molecules will give 1 full mole of chlorine atoms. Then almost always the electron affinity of that non-metal is negative, or I should say exothermic, so it falls down this hill a little bit. And to add an electron to the chlorine atoms, 1 mole of electrons to 1 mole of chlorine atoms. And I know this number, 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 but I don't know this number, and that's what I'm trying to get a handle on. Interesting. Hopefully by you watching this video, number 1, you'll become more comfortable with this, familiar eventually, but you might also come up with a good question to ask. By the way, let me show you this couple of examples of how thermochemists use fractions to balance equations. It's, I suppose, in an effort to only have 1 mole of a product. So usually I balance the equation like this, but if I divide this by 2, divide this by 2, divide this by 2, I get this. That gives me only 1 mole of sodium chloride, which allows me to speak of the energy change associated with forming 1 mole of sodium chloride, 1 mole of formula units of sodium chloride. Similarly, I balance an equation like this, but if I divide it by 2, divide it by 2, divide it by 2, I get 1 mole of potassium oxide. Balanced equation, divided by 2, divided by 2, divided by 2, and I get this. That gives me only 1 mole of iron oxide. Balanced equation, divided by what number? 8? Goodness gracious. Divided by 8 to get this, divided by 8, divided by 8. That's totally weird. Balancing it. We're not really balancing it with the fraction, but we're ending up with a fraction 1/8 of a mole of this, 3 moles of this, 1 mole of this, 2 moles of this, 1.5 moles of this, 1 mole of this. Balance the equation, divide by 2, divide by 2, divide by 2. This is how a thermochemist might look at an equation. Let's try another one. Aluminum and bromine. Goodness gracious. Hopefully you can see that, or you can blow it up. I'll blow it up again. You can blow it up on the PDF if you want. Aluminum solid. Let's melt the aluminum. Let's boil the aluminum. Let's make the aluminum an ion. Once, twice, thrice, taking away 3 electrons. That's the aluminum to get the aluminum solid up to the aluminum gas phase ion. Let's take the bromine. Oh yeah, do you see why that's a 3/2? If you understood that in that previous slide up here, you see why that's a 3/2. Take the bromine liquid, and oops, where are we at? Right here. Take the bromine liquid, 1.5 moles of bromine liquid. Let's vaporize the liquid into a gas. Let's take those bromine molecules and break them up into... I may want to make a change to this. Break them up into bromine atoms. Let's see, if I had 2 bromine atoms per molecule and I had 3 halves or 1.5 moles, that would, Scout's Honor, give me 3 moles of bromine atoms. I see. You know, if I were doing this calculation, and I really should go back and change this on the PDF, I will. This electron affinity for bromine is adding 1 mole of electrons to 1 mole of bromine. Since there's a 3 in front of this balanced equation, I really should take this number times 3. Because I have 3 moles of bromine, I want 3 moles of electron affinity, or the energy associated with that is 3 times the energy associated with 1 atom, or 1 mole of bromine. I don't know if that makes any sense. I got to go back and change a couple little dealios. So being consistent, I should take that times 3. My intention here is not to trip you up with little stoichiometric tricks and coefficients and factors, but good to think about. And so, how does this all fit together? Well, almost always, the delta E, the change in enthalpy or energy follows these conventions or follow these trends. I got to add energy into the aluminum to melt it. I got to add energy into the aluminum to vaporize it. I have to add energy in once, twice, thrice to make ions, take away electrons from that aluminum. So many terms are positive, but a few terms are negative. Usually the electron affinity is negative, and the lattice energy is hugely negative. And because that lattice energy is so big, that will probably drive this to be also very negative. Let's try another one. This is so much fun, I can't contain myself. Let me just look at it. There's where I went ahead and took it times 2. I should go ahead and do that on the previous one to be consistent. If I have I2, dissociate the I2 into iodine atoms, then I have 2 moles of iodine atoms, and if I'm giving 2 moles of electrons to those 2 moles, the electron affinity should really be multiplied times 2 if I'm keeping track of my stoichiometry properly. Interesting. So in other words, this plus this plus this plus this plus this plus this needs to equal this. This direct route versus the scenic route up here. Let's see, do I have one more? I have one more or 2 more? How many more do I have? Oh, yeah, 1 more. Thank goodness, I'm almost at time. This one takes potassium and oxygen to make potassium oxide. So in other words, I start here with potassium and oxygen in their standard states, normal states. Potassium is a solid, oxygen is a gas. Just take half a mole of that, so I get 1 full mole, 2 moles of potassium, half a mole of O2 to get 1 mole of oxygen atoms. So this is directly measurable, and I'm going to compare this, to melting the sodium. Oh, here I sublimed the sodium. I melted it and boiled it at the same time. Sodium, potassium. Hello, K is for potassium. I ionize the potassium. I dissociate the oxygen molecule into atoms. The first electron affinity, interestingly, is negative. But, well, that's not interesting. That's, usually it's negative. But the second electron affinity of oxygen happens to be quite positive, which is interesting. We could wave our hands in the air and try to explain that, but it just is, as measured in the lab. Look at that huge lattice energy of potassium oxide. And again, the terms must all add up. So this being so negative will probably force that to be negative. A little bit positive, a little positive, a little positive, a little negative, quite a bit positive, and quite a bit negative. Alright, let me change that and I'll post this PDF. And thanks for watching, guys. See you in class.